Good morning, Professor Atiyah. It's such a pleasure to have you here chatting with Jianshu and myself. Your talk was simply wonderful yesterday, and I had this last-minute inspiration to have you come here to inspire us further. Just to start off, it's very informal, it's just a chat.
Yeah.
Have you enjoyed your stay here and chatting with our colleagues?
Yes, very much. I enjoyed it. It's been a short stay, but I've been worked quite hard. I've talked to a lot of people, and after my lecture yesterday, a lot of students came up and asked me questions, and that was quite nice. And this morning, I talked with the colleagues from the maths department, and enjoyed that too. And yeah, it's been very interesting. And looking around the campus, it's a nice campus. You've got beautiful views, and and being all in one place, so one concentrated effort is a bit unusual. It gives you an impression of sort of, you see the university much more obviously. So it gives them character. It makes it different from other places. Yeah, it's very nice.
Among your many other positions, I know you've been director for the Newton Institute for a long time, and we're trying to establish an institute for advanced study at this university. Do you think that there is a chance for us to succeed in attracting the best people, in making this become a very vibrant intellectual community?
Yes, I think there is an opportunity. I think there's so long as one has a clear vision of what particular function this institute is supposed to perform, and I think the President explained to me what he has in mind, then I think it is possible to aim to attract good people and build it up. It's very important, but of course you have to be very careful of the choice of people. For example, the institute in Princeton, which I went to when I first got my PhD, the first person they appointed was Einstein. Then they appointed Hermann Weyl and von Neumann. So I mean, it's important to get really good names, and you have to work hard. And it's probably more important to identify people than to define subjects. Then you choose the good people, and then they will determine the exciting areas. So I think it is possible, so long as you're clear in your mind what it is that you want to do, and so long as it fits in with the sort of needs and interests of the area here in Hong Kong. There's some particular things that are of interest which can attract. But then obviously I think that it's an exciting idea, so I'm very glad to be asked to join your advisory board. I will follow with interest the developments. I've been shown where the site will be, a very beautiful site on the top of the hill. It's important to have a good site for an institute because it helps to inspire great ideas.
So let's say we want to be a Princeton, a Cambridge, and there is an Einstein out there. How do you think we could persuade Einstein to come?
Well, I think that you have to choose the right combination of circumstances. Even Einstein, Princeton managed to get Einstein because he was in Germany and the German situation was getting bad with the advent of the Nazis, so it was an opportune moment. Otherwise, even Princeton couldn't have got him to go. He wouldn't leave Germany. So I'm not saying that you have to wait for a similar situation, but you have to be opportunistic. You have to sort of look at the world, and whatever places, situation, people, and then you can't expect anybody to come where you want any time. But so you have to choose carefully, and you prepare the ground, and you may not get Einstein, but there are other good people besides Einstein. So I think it's a question of choosing the right person, the right time, being very skillful, and not being in a hurry. Don't say we have to have somebody here by the 1st of January. We'll turn the first person in the street, and we'll bring them inside. You've got to wait a little bit. If necessary, you postpone while you have your time. Make sure you don't make a mistake. It's nothing worse than to make the first initial appointments at a lower level, then everything goes down. You've got to make sure the first appointments are very high level, very high prestige and visibility and things. So it's important. It's possible, but it requires some skill.
Yeah, that's wise counsel, which is very foreign to Hong Kong.
Yes, they're always in a hurry in Hong Kong, in a hurry. Patience is important.
Well, we have, I think our students have enjoyed your talk very much, and our colleagues already benefited enormously from talking to you. It's really inspiring and very wonderful experience to have you here. The first question I want to ask you is, we're inspiring to build an institute as modeled after the Institute for Advanced Study at Princeton. What are the factors that made the Institute for Advanced Study at Princeton so successful, and what common features we share with them and we don't share with them?
Well, I think first of all, you have to remember that the Institute in Princeton was founded in the 1930s. It was more or less the only kind of institute of that type anywhere in the world, so it had a unique situation. It also was fortunate that they got a big endowment from the beginning, and there was then all the trouble in Europe with Germany. So lots of factors helped to get it started. And I think every institute since then, there have been many institutes founded around the world since, and they're all different. They're modeled in broad terms on Institute in Princeton, but each one has to have its own particular aspects. It has to relate to the society which it is, and institutions, and so you don't copy a thing exactly. You just take the idea and then adapt it to your own circumstances. And so here, this has to be adapted to what is appropriate for Hong Kong, and you have to make your own efforts. But still, some things are common to all these institutes. They're all fundamentally institutes where people do theoretical work. They don't tend to go in for institutes which involve big laboratories, because if you do that, then you have to have very large buildings, a lot of expense. So they're all, the Institute Princeton, it had mathematicians, theoretical physicists, then people in the humanities, classical scholars. It was not just mathematics and science. But they're all people who you don't need much except some brains. If you do that, then that rule makes the problem a little simpler. You don't have to have big equipment and laboratories, and so that determines the scale of the institute can be of a certain size. Otherwise, you have to become MIT or Caltech and very, very large institutions. So that will be one common feature which I would expect similar institutes to develop. They're on the theoretical end of whatever it is, mathematics, science, or if you go into other fields also, business, or and it has to be the sort of the intellectual end of the thought, which is easier in a way. It doesn't cost so much money, you don't have big buildings, and it's perhaps easier also to pick up the really key individuals, because they made their big contribution, and they don't depend on teams of large, experimental science has big teams, laboratory. It's hard to perhaps identify single individuals, but in the more theoretical end, individuals stand out. So I think that feature will be common, I think, to all such institutes. Beyond that, I mean, institutes function differently. Some have a lot of permanent faculty, senior people, and then at the Institute of Princeton started off with the permanent faculty, and then later they found it useful to bring in postdocs, younger people, visitors, and this grew and grew and grew. They got more money for these things, and so now much of the activity, or perhaps most of the activity, takes place amongst the visitors, younger people. Permanent faculty are there. Their role is amongst to set the standard and to invite younger people, but the activity is much wider than the permanent staff. Other institutes have even less permanent staff. The Newton Institute in Princeton had a very small, just the director, assistant director. Other than that, it had a rotating staff, and it also had different programs. We specialized in different fields at different years, and we were trying to be interdisciplinary to mix mathematics and all sorts of other fields. So that was our particular definition of our role. But other institutes define their role in a different way. They may have different. I think talking here to President Chu, I think I get an idea of what is this kind of natural focus here in Hong Kong, to focus on sort of the high-tech side of new developments in science with potential applications to the economy, and therefore bringing also a combination of the sort of business community and the scientific community. And so a mixture along those lines, which is of high quality, which would be sort of relevant for Hong Kong. So I think every institute has its own particular center of gravity, and then it develops its own way of, or often also depends on the kind of finance it gets and the relationship with the other thing is that also whether it has a relationship part of a university or not. Here, this is part of the university, which has a lot of advantages. And the young people in the university can attend the seminars and lectures and benefit. And it's very important that the doors should be open so that if you're a visiting speaker gives a good lecture, then any students from any faculty who are interested can come, even the undergraduates or graduates. In Cambridge, the institute there was technically part of the university, and it was independent, autonomous, but legally in part of the university. And it was open, students would come from the university to attend. Other institutes, sometimes like the Princeton Institute, is not part of the university. It's not far away, it's only 10 minutes by car or half an hour by foot. But it's institutionally separate, it's different finances, different government, everything. So that's quite separate. So they have different possibilities either, but it's close to the university, and so they can benefit. So the relationship with the university, or maybe several universities, is quite important, because that's where the young people come from. Or there are a lot of local people, young. You can invite postdocs and young people internationally, but if you want to benefit the local community, then it's the young people in the university who should be encouraged to take part and attend and get inspiration from the institute. So the institute has a big role to play in terms of inspiring younger people. When I was in Cambridge, I was very much surprised we would have these programs which were theoretical now, but they were interdisciplinary, and sometimes we would get people from many departments, engineering or biology, who would come, and they would suddenly be inspired, and they would become at the beginning of their studies, and then they would work on these new fields right at the beginning, and then they would lead them on to later careers. So it kind of if you catch a young person at the right period of their development, and you inspire them, you can have disproportionate influence. It can really change their life and their careers. So that's a very big opportunity, and the institute in the university can play such a role over and above what the university can do. So there's a big potential.
So thank you very much for your advice, and I'm sure you speak from experience, and we're looking very much forward to your continued advice.
Well, I'd be glad to. Always easy to give advice.
I actually wanted to go back to your talk yesterday,
Yeah.
which was fascinating.
I'm glad you enjoyed it.
You mentioned beauty as something that ties together the arts and humanities
Yeah.
and mathematics, for instance. What was interesting to me was that you didn't mention truth. I would think that mathematics or sciences are focused on seeking what is true.
Actually, thank you for reminding me, because I meant to say something about that, but I was short of time. Of course, in science and other things, truth and beauty are two prime objectives, and they go together. In fact, truth is part of beauty, and beauty is part of truth. But so, if you're writing or you do poetry, the two things are there. Now, people would say, well, in science, scientists must believe in truth, and they have to make a choice. They should go for the facts. And if you're an artist, you can choose. You can choose to go for the beautiful things and ignore and that's not quite right. In fact, the famous mathematician Hermann Weyl, who I mentioned before, who was at the Institute, he wrote very well, by the way. He had very good style. And he said, in my research, two guiding principles are beauty and truth. But if I have to choose, I choose beauty. And you see, the reason is, I think there's a very good explanation. You see, truth is objective, beauty is subjective. But objective truth is very difficult to find out. What is truth? You think you know now, the facts may turn out different tomorrow. You may be wrong. Truth is there, but you don't know the truth. You only try to find the truth. Beauty is in here. If I think something is beautiful, you can't argue with me. And so I'm right. You are absolutely certain that the thing is beautiful. If something appears to you to be true, it may not be true. So if you have some choice, you're doing something, and truth seems to be this, and beauty tells you that, if you choose beauty, you may be correct. And in many cases, in one famous example, in fact, Hermann Weyl's own work, he did some piece of work in the beginning where he was trying to explain electromagnetism in terms of relationship to geometry related to general relativity, and he put forth an idea which is beautiful. But Einstein pointed out it was wrong, because its physical interpretation, you could contradict the laws of physics. And very interesting, but Weil still believed in his paper. The paper was published, even though, and Einstein's objection was published as an appendix. So there was this paper which is wrong, Einstein showed it was wrong, and it was published. And actually it turned out that the paper, with a slight reinterpretation, was true and correct, and became the foundation for all subsequent physics. So it's an example that, you see, the definition of what is true is not something we know. The truth is outside in the world, and we only see parts of it. So when you say you think you found the truth, that you're not sure. So whereas beauty, you are sure, because you are the ultimate judge. You know, they say, he said, beauty is in the eye of the beholder. If I think something is beautiful, it is beautiful to me. And that's my work. So there's a very good reason why, I mean, in some sense, deep sense, beauty is a better guide, or can be, not always, you can be misled by mirage, a better guide for the individual. And that's why I've been, my work, not as famous as Hermann Weil's work, but on one occasion I had some problem I was working on at a conference, actually, and I had this beautiful idea. I tried it out, looked very nice. Then there were some experts there, who expert in some field, where we could test the idea. So I said, "Will you hear this? Test this idea and see if it works." They went away. They say, "Sorry, it doesn't work." Now I could have given up, but I believed the idea was so beautiful. I didn't believe them. And I went back and I tried hard, and I was right and they were wrong. You see, if you have a good feeling that something is true or because it's so beautiful, then you may be right. So you mustn't be put off by the first attempt. If something seems to be hit a brick wall, that's really the way to get around that. So I think beauty is a very, very important guide for people in mathematics. This is the way. This is how we choose what distinguishes one theory from another theory. We go for something which looks fundamental. You see, what is science? It's science that describes the complicated world in a simple way that we can understand. You try to reduce all the variety of data to some simple principles, laws. Why? Well, we think that it's easy to understand. In principle, if I have any formula that would explain the world by just putting it into a machine and turning a handle, if you only want the practical answers, that may do. But we want to understand it in here. So you have to make it small enough to go into the human mind. And so
it's just the opposite of my understanding of what mathematics is about. This is always going to be objective and true, whereas beauty is something that's emotional, it's subjective.
That is the commentary. I was trying to explain why that view is only partially correct. I mean, everything has two sides. But beauty has a more important role than people outside would think. They would think mathematics, nothing to do with beauty, just, x plus y. But no, beauty is a very, very important role, and my work, it's always guided me in my ideas. And so I think it's quite correct. You compare mathematics with things in the arts. And there's a lot of similarity in some deep ways, in what you search for, how you try to find things. And I was telling somebody the other day, my first name is Michael. I was really called after Michelangelo. So,
so the seeking beauty is in your blood.
That's right, yes.
So help me understand. When you think of a formula, and you think it's beautiful, how do you feel? What is the difference between looking at a formula and thinking that might be beautiful? How might that be different from looking at a statue and thinking that's beautiful? Are you emotionally? Do you feel different when you're looking at the two different kinds of beauty?
Beauty comes in many forms and many shapes. You can have beauty in music, sculpture, art. They're not all the same. There's some common aspects of them. You can try to define it. You can say what are the components of beauty. You can list many attributes, but at the end of the day, that's only a guide. You see the beauty when you see it, you know it's there. But you can make an abstract list of things. Things should have elegance, it should have some simplicity, but it should also have some depth, and it should have some meaning, and it should have some wide scope, and it should have different sides to it. I mean, many things you can talk about, all of which are, in some broad sense, true for all kinds of beauty. In mathematics, you can apply the same general principles of that kind to mathematics. It should have, And I tried to give this example. There's one formula I wrote down, e to the pi r equals -1. It encapsulates to a mathematician so much information of a deep kind in such a simple equation. That is, ultimate example of beauty in mathematics. The ultimate example of something which is ugly in mathematics is a big page of formula of algebraic equations where you can't see anything at all, which you find very often in the published papers.
Well, like the hieroglyphics to me, that's beautiful.
Well, no. The beauty is simplicity. A complicated, messy formula is not beautiful. I mean, you must be able to see at once the meaning and understand it. And you must try. Of course, you can try to reduce complicated ideas to simple forms by finding ways to package it into small pieces. But you can't have disorganization. Mathematics has to be organized, controlled, and tightly related into sort of very well-defined pieces. And the beauty consists in how beautifully these are made, like polished diamonds. And there's a lot of mathematics. The beauty is also it's a bit I like in architecture. Architecture, you see, you have a big building, and it can be beautiful because you stand back and you say, what a marvelous skyscraper or castle or cathedral. Is it because it has big vision, and mathematics has some big theories like this, beautiful logical structure. But then it can also have beauty in the detail. You could have beautiful, in old cathedrals, you have beautiful carvings, or a bit of stonework, or very fine skill of the craftsman. And mathematics is the same. The details are very important, and they can be put together in a very, very precise, elegant way. So you can have small-scale beauty and large-scale beauty, and a really beautiful thing have them both put together. So and so you can make many analogies. I like architecture and mathematics are very good to explain the analogy because, see, architecture, they have a building. A building has a function, some purpose. Not just for, or sometimes it was just, if it was a temple or a palace, it was just for glory of God or something. And the mathematics has large parts of mathematics will have some utilitarian purpose. Calculus was invented to explain dynamics and planets' motion, so they have function. Mm-hmm. But then a building also has architectural beauty. Mathematics has its beauty and its poetry, and then it has this detail, small scale, large scale. And also, architecture changes with time. There's new technologies. The old days you built with bricks or stone. Now you build with steel and glass or plastic. Every generation there's new technology, new way of building. And each new kind of building gives you different possibilities. And same is true in mathematics. There's new machinery, new intellectual sort of machinery, like the equivalent of inventing new technology in glass or steel. So we invent new machinery, and this enables mathematics to build more complicated buildings, big skyscrapers, which in the old days you couldn't build. So there are lots of analogies between architecture and mathematics where you can begin to see the parallels in a way that, if you understand the one, it helps you understand the other one.
I see.
As a mathematician, I have no difficulty understanding that mathematics, or at least good mathematics, is very beautiful. But sometimes I find it difficult to explain to people why government and society should support mathematical research. For example, we don't produce commercial products. Our typical graduates don't necessarily make a lot of money.
Some do.
Yes.
On Wall Street.
Well, I think this answer is, first of all, the answer you can ask about many things studied in universities, not just mathematics. Very pure basic science is not directly commercial. If you can study history and philosophy and literature, these don't immediately make money. So mathematics is part of the whole process of knowledge, learning things. And so from one point of view, it's necessarily part of civilization to educate people in all sorts of ways. But then, of course, it has a utilitarian side, which is to make practical things which you can sell. And mathematics you need some mathematics to do elementary things. To be an engineer, to be a physicist, a technologist, you need quite a lot of mathematics. And in universities, many members of the mathematics department faculty teach people who will become engineers. And now many will go into the financial world and make money. And they need some mathematics, sometimes now quite sophisticated mathematics, financial mathematics, working on the stock market. They need and then nowadays you also, if you go and work for a bank and you have to establish some security system to make sure that nobody breaks into your credit card. That's based on really very abstract modern mathematics, theory of prime numbers and so on. So large parts of mathematics are actually used in the outside world. Sometimes people don't know it, but they don't realize it. And all modern technology and these lights and the television cameras, they all rest on laws, Maxwell's equations, which are written down in mathematical form and sophisticated mathematics. So mathematics is part of modern civilization. It wouldn't exist. So I think there's no question that mathematics has to be taught in any advanced institution which is serving society. And the thing about mathematics, it's studied in many, many ways. More than, it's like, I said in my lecture, that mathematics is like a language. And just like you teach English or you teach Chinese for people, anything, you need language. Because you need to explain, you need to. Mathematics is similar. It's a language. It's a language that underlies large parts of society at the technical level. So mathematics is the most widely, probably, used bit of what people study in universities. Physics, chemistry, biology, all used in rather more narrowly defined ways. Mathematics, in principle, can be used anywhere. So in that sense, it should be the easiest to explain. Now, when you ask me about the relationship of beauty to this, I think the point is this, that what society gets out of mathematics is what I explained, the general applications of mathematics in a whole range of fields, and the fact that they need trained people who can both work and make productive things, and also intelligent citizens who can understand how to vote, how to calculate. So you need the people to be trained in mathematics, perform this role. But on the other hand, the individual mathematician, you or I, doing our research, we are guided in our choice of work, not by necessarily the utilitarian aspect. We don't work because we think it's going to, because in fact we don't know how it will be applied. You follow the mathematics by itself, and you choose the problems because they look mathematically interesting, because you enjoy them, and the beauty leads you in the right direction. And we found from experience that if you let mathematicians choose what they work on, then they produce the best results, which will, in the long run, be the important ones. If you tell somebody to make something here and now, he makes a table or a chair, but he doesn't make, electromagnetic waves. They come after the long theory. So this applies to basic science as well. Experience shows that you let the scientists follow their own imagination just for curiosity or for beauty, whatever it is. This way, you get the most practical results. If you go for the practical results, you get only low-level practical results. In the old days, you might say that if you were designing vehicles, you had carts and horses, and you could say, well, we should improve the wheels, better wheels. But the next transport didn't depend on superior wheels. You've got motor cars and aeroplanes, which based on different principles. So just improving what you have by practical purpose, if you focus on what you think you need now, limits your horizons. You never get to the next stage. You never get to a quantum jump. Those big jumps in progress come from imagination. And imagination is very much related to beauty. I know where does the imagination take place? It takes place in the head. You have pictures, visions. These are the things that enable you to really leap forward. If you just focus on what you want to do here and now, you just get a better chair and a better table. You don't make real progress. So it's very short-sighted to focus on what seems to be the most practical. The really important in biology, all the great progress in biology came from people working on molecular biology in the beginning, and nobody had any idea that you could have any application. It was just curiosity. What is it that makes life work? And also the beginning, famous example of Rutherford when he split the atom. Something he said, this will never be of any use to anybody. We just do it because we want to know how atoms are made. Well, now we have atomic energy, whether you like it or not. So the consequences of pure thought have proved to be spectacular. And so this is a long experience of civilization. You must encourage freedom of thought. Freedom of thought is important both in the political context and in the scientific and literary context. You must have imagination to see the future and think your own way. And this all comes from allowing people to think freely. If you try and order them, do this, do that, you don't get any success. They don't like it. They don't do good work. You have to allow them to be free and follow their own inclination.
So perhaps what you just said also explains the contrast between ancient Greek mathematics and ancient Chinese mathematics.
Yes.
That the Greek mathematics tends to be more theoretical and for the curiosity and for the philosophical meaning.
Yes.
But Chinese mathematics tends to be very practical for the measurement of land and so forth. But if we look at the results today, that mathematics has really flourished in the West, and in China we're catching up in the last couple of centuries, and we're still doing that.
Well, I think it's a good example, but I'm glad you said so, not me, because but it's certainly true that Greek mathematics, I should say two things. Greek mathematics always regarded as the best, fundamental beginnings of modern mathematics, because the reason they give, I think, is not quite the right reason. The reason they give is that they were the first to formalize the notion of proof. You prove something because you give an argument that shows it has to be true, instead of just saying, well, here is one triangle, I've measured I checked Pythagoras' theorem by working it out for hundreds of triangles, and I say, well, it has to be true because it's true because you demonstrated it. And in the old days, that was the way mathematics was done. You found out by experiment something worked, and you got a rule, and you didn't look for a fundamental proof. So the Greeks produced a notion of proof, which is the way it's a kind of, and proof is a kind of essential cement that enables you to build a building that doesn't fall down. If you build a building without putting something like cement, after you've got a few layers, it topples and wobbles, the foundations are not safe. And that is important. But it is the other side as well, really. The Greeks were interested, I think, out of curiosity. They would ask questions about circles and triangles which had no obvious practical application. And then they would try to prove them. And so they were the beginning of curiosity-driven research. And this was what led to the theories later on and became the foundations of modern science. And I said, I think I mentioned this or here or somewhere else, that the best example of the long-term impact of this, the Greeks discovered about ellipses, and they studied the ellipse because it was nice study. And then it turned out more than 1,000 years later that the ellipse was what you needed to describe the motion of the planets around the sun. But if the Greeks hadn't done it, somebody else would have had to work it out much later on. But they did it because they enjoyed liking conic sections, beautiful things, and they proved marvelous things about them. And that was the beginning of So I think you're right in the sense that was why mathematics regards the Greeks as their source, because it was built not on practical applications. Before that, mathematics did exist, but it was tied to practical things, putting up buildings, measuring fields for agriculture, or even paying taxes. Arithmetic was developed to count out the money to pay the king's tax. But those had a very limited, they didn't lead to a great deal by themselves. And the Greek input was, I think, I don't know the history of China so well, but what you said sounds that might possibly be right.
So the lesson is to indulge in this pure thought.
Yes,
and enjoy it, and encourage people to do that.
That's right.
And then maybe several thousand years later, people will find use for it.
7,000, it need not be 7,000 years later. I'll give an example where it was, but of course things move much faster now. That was, very primitive time, but now things are growing so fast. Now we have the opposite extreme, where in only a few years, something which is fundamental science finds a practical application. So the time scale it can be unpredictable. Something might well wait for 50 years, even now. But it can move much faster. It can be only 5 years or less. 1,000 years is probably unlikely now, because things are so much faster in information. But you can't predict, you can't guarantee. And some things, perhaps, of all the things that are done by pure mathematicians, I can't say that everything will find some important practical application. No, you can't say that. But increasing numbers, larger and larger parts, find unexpected applications. And when they're unexpected, it maybe takes longer. And some parts may never be applied, but then there'll probably be a small part, and it's a small loss in the big investment. So, if you gamble on horse racehorses. The jockey club here is very important. You don't always win, but you win enough times if you're good to succeed. So investing in ideas is a bit like that. You cannot be sure that every idea will... But because things like mathematics is very much interrelated, mathematics is all full of interconnections. It's not one separate lot of buildings. They're all connected, like a bit in Hong Kong. You have all these crossways, and therefore an idea can move up, down, sideways, and it can. So you can't say this bit is no use because this bit was connected to this bit. So it helps. So I think the fact that mathematics is really one total theory in some sense, all interconnected, means that every part of it really contributes. And you can't tell which part contributes to which in the end because they all interact so much. So I think you can justify mathematics very easily in terms of its coherence, its impact, its applications, and its unity, and yet the same fact that it also has this enormous range of potential. Now, we know the mathematics has been very useful in the past for all sorts of science. Now it's being used in social science, and biology is coming in, big future. So lots and lots of areas where and there are always new ones. As I mentioned, this business of applying prime numbers to coding, which you use to make your credit card secure in the bank. This is a very recent technology, I mean, only the last few years. And before that, this was regarded as a very, very pure part of mathematics, the ultimate example of the useless bit of mathematics. Some famous mathematician said, I like prime numbers because they will never be used, you see. It's totally safe. He didn't like things being used because he thought if they were used, they'd be used for bad purposes to kill people, and so he was doing something totally safe. But I think, well, unfortunately, prime numbers can be used for not only security codes for banks, they can use security codes for the military as well. So, there's always two sides to the applications. They can be used for one purpose or for another. The mathematics is sort of neutral in that respect. But it is surprising how many things have applications which you can't predict.
Well, nobody has conveyed to us, to me, such joy or such excitement of mathematics, and I really feel as if I'm in the presence of an artist, someone who's totally convinced and excited about his work. And I thank you very much.
Well, I'm glad you got that impression. I mean, I certainly, I spent my life doing mathematics. I enjoy it enormously. I feel very privileged to have had the opportunity, and I'd like to convey this to other people, not only to other mathematicians, not only to students, but because the general public, the general view is mathematics is difficult, hard, not
or self-indulgent.
So I wanted to show that no, mathematics is about things which are common to other people. Its relation with art, it inspires people, it's exciting, and it is important. So this was the message to the general public, and I'm glad that you got the message.
Thank you very much.
Okay, thank you.
We are very grateful. I'm particularly grateful that you are here to explain mathematics in a way that's much better than I could do myself, with a lot more authority too.
Well, I'm very, very glad to be able to help, and I'm glad my visit has been successful in that respect. Thank you. Thank you.